Welcome back. This week, we're diving into a really fascinating submission. It's a highly technical manual on managing oxygen transfer in Pichia pastoris fermentations.
And it's all built around a pretty catastrophic scale-up failure.
Exactly. The engineering here, the data, it's absolutely outstanding. Let's just jump right in on how we can shape this into a more compelling narrative.
I agree. I mean, the listener has a fully fleshed out diagnosis of a huge industry problem. You've got this deadly synergy between metabolic heat, the oxygen uptake rate,
Right, the OR.
and the plant's physical limits, specifically the kala. So the challenge is really moving from, documentation to something more like dramatic communication.
Okay, so let's start with the first big idea. I think reversing the sequence of the case study and the technical deep dive would just maximize the impact of that Blue Horizon failure, especially for a spoken word format.
Mm-hmm.
So a key theme that runs through this is the core philosophy. Biology does not scale, physics scales.
Right. The golden rule.
And the current structure, it puts this rule right up front. Then you get the case study, and then finally, the deep dive on why it failed. It's logical. It reads like a textbook.
It's perfectly logical. And, if this were an SOP manual for new engineers, you wouldn't change a thing. But for a critique aiming to really engage a listener, you have to lead with the drama.
You have to hook them.
You have to hook them. We need the audience to feel the urgency of that failure before we give them the diagnosis. Right now, you kind of risk losing people before you even get to the good stuff, the payoff.
I see your point, but won't that confuse the specialists, the engineers who might actually prefer that deductive rule-first approach? How do you balance the narrative tension with, clear technical teaching?
That's the thing. It's the core adjustment. You don't sacrifice the teaching. You just flip the sequence. You make it inductive. You need the audience invested in that 60% titer drop, the proteolysis.
The absolute disaster.
The failure itself is the hook. Instead of presenting that table, the lab versus plant performance, as just, diagnostic data, you frame it as clues. Clues the engineers on the ground had to hunt down.
Okay, so the suggestion is a big structural shift. Start with the outcome, the catastrophic 12,000-liter batch. Then use that cold, hard data to build a mystery around these hidden variables.
Exactly. And only then, when everyone is asking, why, do you introduce the core philosophy as the big lesson learned, the truth they discovered through that failure.
Right. Let's look at the numbers. The data shows the plant's max KLA was what, about 350?
350, inverse, yeah. While the lab process was demanding 800.
That's a massive gap.
A huge gap. And that physical constraint, that's what proves the golden rule. So you structure the story so the audience discovers that discrepancy right alongside the original engineers. It becomes a reveal.
Okay, but how should that discovery moment actually sound? I mean, a lot of people in the audience won't immediately visualize what KLA even is.
Good point. At its core, KLA is just the speed limit, right? It's the maximum rate the tank can dissolve oxygen into the liquid. It's a physical constant.
So you frame the failure around what happens when you hit that limit.
Precisely. The moment your dissolved oxygen, your DO, hits zero, the organism's metabolism changes. That methanol they're feeding, it can't be consumed properly. It just starts to build up.
And that leads to the toxic formaldehyde accumulation, the AOX pathway intermediates. That's what kills the cells and triggers the protease release.
Yes, that's the climax of the story. The fixed KLA is the immutable law of physics, the methanol feed is the violation of that law, and the formaldehyde and proteases, that's the dramatic, irrecoverable consequence.
Now, what about the heat? I'm really intrigued by that. The material mentions the temperature drifted up by 2 degrees Celsius.
Yeah, and that temperature spike is the thing the plant engineers saw first. It's tangible, but it's a symptom, not the root cause. So, a really effective way to structure this is to open the whole thing with the heat spike, the panic on the floor as the cooling jacket maxes out. Because that feels like a problem you can solve.
But you can't.
But you can't. Because then you reveal the silent killer was the drop in the surface area to volume ratio, the AV ratio. That's what made heat removal impossible in the first place. You lead with the visible symptom, and then you unravel the invisible physics that caused it.
That really does make it feel like a thriller, not just a tech report.
Exactly.
Okay, let's move on. To successfully address the non-specialist scientists in the audience, the detailed physics of this failure needs a single, cohesive, non-technical mental model. Something that links oxygen, heat, and mixing.
Right.
I mean, the material is fantastic on the technical mechanism. It makes a really strong case for the OTR mismatch, stating that Pichia on methanol generates 2.5 to 3 times more heat than on glucose.
Per mole of oxygen, yeah.
Which puts you at this huge risk of the oxygen uptake rate, the OUR, exceeding the tank's maximum oxygen transfer rate, the OTR max.
The technical depth is absolutely superb, but, it presents 3 distinct, very mathematical challenges. You have oxygen transfer, heat removal, and mixing time all as separate things. For a listener who's not in the weeds with this every day, that's a lot to juggle.
It's cognitive overload.
It is. I mean, is there a risk that by focusing on the individual equations, like OUR versus OTR, we miss the chance to give the listener one simple picture of the combined stress on the cell?
So what are we suggesting here? An analogy?
I think we need to design an original extended metaphor. Maybe a supply chain or a traffic jam analogy, where these 3 hidden variables, oxygen, heat, and mixing, are all just constraints on one single system. That way the connection between, say, Cl star and the AV ratio feels intuitive, not just mathematical.
Okay, I like that. Let's flesh out the hyper-efficient factory analogy. How would we make that work in conversation?
So we frame the 12,000-liter tank as this hyper-efficient factory. The workers are the Pichia cells, just cranking away at max efficiency.
Okay.
In that factory, the CLA, that's the ventilation system. It's how much fresh air you can physically pump in. The AV ratio, the surface area to volume, that's the building's insulation rating, how well it can shed heat.
And a product contamination is where it all comes crashing down.
Exactly. The moment your feed rate demands an oxygen uptake that exceeds what the ventilation can handle, the factory floor becomes toxic. That's your formaldehyde. The workers panic. They die. They release proteases.
Product contamination.
And there you have it. One single picture that links the oxygen limit, the heat problem, and the quality disaster.
That is very strong. I like that. What about the mixing, though? The 90-second lag time. How does the factory handle that?
That's the delivery lag. Or maybe the management response time. If your mixing time is 90 seconds in the big tank versus 2 seconds in the lab, your diostat controller, the thing that's managing the methanol feed, is basically reacting to old news.
It's flying blind.
It's flying blind. It gets a low DO reading, so the feed pump slams the gas pedal. But by the time that methanol is actually mixed through 12,000 liters, the culture has already hit starvation pockets.
And then it overshoots.
It wildly overshoots, and then it has to slam the brakes when the DO spikes back up. It creates this violent, cyclic instability that the organism just can't handle. The factory's being managed by a controller's response time is completely out of sync with the physical size of the building.
Okay, third point. The crucial training provided in the SOP section on OTR capped feeding should be framed as a core philosophical choice about process control versus biological demand to really emphasize the industry impact. The solutions provided are great, very actionable. The OTR cap calculation, the troubleshooting guide. As I understand it, the solution is purely mathematical. You calculate the plant's capacity, you derive the feed limit, F max,
And you cap the biological demand. You make sure OUR never exceeds OTR max.
exactly.
And that's the technical endpoint, yes. But the transition from the dramatic failure, that attempt to hit 120 grams per liter cell density, to a prescriptive SOP, it's a bit jarring.
How so?
Well, the core insight is profound. Do not feed the organism what it wants. Feed it what the tank can breathe. That's a huge philosophical statement, and it gets a little lost in dry procedural language like step 1, step 2.
I see. So we're moving from just following a procedure to adopting a strategic engineering mandate? But what's the real benefit of reframing it that way? Aren't we just telling people to accept lower titers for safety?
We're refining the very definition of success. It's not just about philosophy. It's about accepting, say, a 10% lower theoretical yield today to guarantee zero batch failures tomorrow, zero regulatory rejections, 100% stable critical quality attributes.
So the suggestion is to use these technical solutions to open up a bigger conversation about risk tolerance, quality assurance.
We need to be talking about designing for a safe failure mode, not just designing for a peak theoretical titer that you might never hit reliably.
Which makes that F-max calculation, it's not just a process limit, it's a critical quality assurance tool.
It's the whole game. We have to emphasize the moral of the story from that consultant's note. The engineer faces a career-defining choice, right? The lab data says the optimal feed is 7 liters per hour.
But the tank can only handle 5.
But the tank can only handle 5. That disciplined, difficult choice to clip the feed at 5, that is the defining moment of successful scale-up engineering. You're sacrificing immediate growth for long-term product integrity.
So what looks like a failure to meet a target in the short term is actually the ultimate success in bioprocessing.
That's the takeaway. And you can even take it a step further. Look at the section on scale-down models, the bad mixer and K-law constraint tests. You're engineering failure on purpose in the lab.
To prove robustness, you're forcing the DO to drop to see if the process can handle it before you risk a 12,000-liter batch.
Exactly. It makes the whole discussion about designing for failure, not just for success. The long-term fix isn't just turning down the feed pump. It's fundamentally reducing your peak cell density targets in future processes to guarantee your CQAs are stable no matter what.
This framing really elevates the material. It turns it from a manual into a strategic manifesto.
That's the goal.
This has been incredibly constructive. So, to summarize the main points. First, we're saying reverse the narrative sequence. Lead with the catastrophe to maximize tension before you explain the physics.
Second, develop that single, cohesive mental model, the hyper-efficient factory, with its ventilation and insulation limits to unify the complexity of oxygen, heat, and mixing for everyone in the audience.
And third, reframe the OTR calculation, that F-max, as a core engineering philosophy about risk. Focus on that disciplined choice to clip the feed, to protect the CQAs, and to design for a robust, safe failure mode.
The technical depth here, the data, it's all exceptional. It's ready for a much broader audience. I can really see what you're going for. Let's just focus on strengthening that narrative delivery, that philosophical frame. We look forward to seeing the revised version.
Until next time, keep challenging yourself to refine your work.